The sun has just done something terrible. A huge hole erupted on its surface, releasing a stream of plasma toward Earth, while the interstellar comet Tri-I Atlas vanished from all telescopes, and our planet experienced an earthquake. Now everyone is wondering, what happened? Was the comet destroyed or transformed? And what will it look like if it reappears? As one comet fades into shadow, another takes center stage. The Lemmon comet, an icy relic older than civilization, races across our sky. We will tell you why the next 2 weeks will be crucial. Meanwhile, in China, physicists have achieved what sounds like pure science fiction, an invulnerable communication network that is an absolute spy. Don't blink, because before we finish, we will unveil cosmic dates that cannot be missed, including one that no one talks about, but should be. If these mysteries keep you as tense as they do me, don't just watch. Act, like, subscribe, and stay with us as these stories unfold in real time. Write a comment about where you are watching from, what time it is there, and directly say, do you believe we are being told the whole truth about these changes in the world? If you want to help our community grow, share this video on social media or in group chats. Every action you take fuels our search. You are the reason we can continue following these stories, so thank you for supporting us in this quest. Part 1. The Disappearance. The sun has just done something terrible. October 2025 began with a cosmic alarm signal that most people did not hear. Scientists watched with growing concern as a massive trans-equatorial coronal hole opened on the sun's surface, like a wound radiating invisible energy into space. This was not the typical solar activity that produces beautiful auroras and possibly disrupts satellite operations. The hole was colossal, encompassing areas of both the northern and southern hemispheres at the same time. Such occurrences are very rare, with consequences that we are just beginning to understand. The solar wind, bursting through this gap in the sun's magnetic shield, reached speeds of 700 kilometers per second. To imagine it, picture a hurricane where each particle of air moves at nearly 1.5 million miles per hour. A stream of charged particles, protons and electrons, torn from their atoms, raced towards Earth like a cosmic hose aimed directly at the planet's magnetic field. The alignment was perfect, almost suspicious. The magnetic polarity of the solar wind matched the orientation of the Earth's field exactly in the configuration necessary for maximum connection. It was the strongest possible transfer of energy from the breath of the sun into our planetary magnetosphere. Geophysicists hurried to predict the consequences of solar activity. Power grid operators received warnings, and satellite controllers prepared for possible failures. Aurora hunters packed their cameras and headed north, knowing that such a solar flare would paint the sky in indescribable colors. But at that very moment, something else happened. What turned this solar phenomenon from a mere episode of cosmic weather into a true cosmic mystery. The comet Tri-I Atlas, only the second confirmed interstellar visitor ever detected in our solar system, vanished behind the sun. In an instant, it was visible. A faint spot of light moving along an orbit that began in another star system, carrying ice and stones formed in alien clouds around a star we will never see. In the next moment, she vanished into the sunlight, absorbed by the brightness of our star, becoming invisible to every telescope on Earth and in space. The time of this event could not be ignored. The Earth's magnetic field was being struck by fast solar winds for several months, while our only available interstellar messenger disappeared behind the source of this impact. Scientists are cautious people trained to avoid hasty conclusions, accustomed to repeating the mantra that correlation does not equal causation. They carefully chose their words when reporters asked if these events could be related. Then the earthquake began. In different regions of the Earth, several earthquakes of magnitude 7 occurred within hours after the arrival of solar wind. The monitors recorded strong tremors, a sudden release of tectonic energy that had been building for years, possibly decades, in the strained rocks beneath our feet. The tremors were not unexpected in a statistical sense. The Earth experiences about 15 earthquakes of magnitude 7 each year, but several such events occurring close in time to a major solar phenomenon and the disappearance of an interstellar comet awaken in the human psyche that ancient instinct to seek connections, demanding meaning from coincidences. Could the magnetic influence of the sun on Earth somehow provoke seismic activity? The main scientific community asserts that no, that's not how the physical processes of earthquakes work. Tectonic plates do not depend on magnetic fields or solar wind. They move and shift according to the laws of rock mechanics and accumulated tension. However, there are other opinions. Researchers at the borders of geophysics point to statistical anomalies in the timing of earthquakes during solar maxima, suggesting mechanisms related to ionospheric coupling or subtle changes in the Earth's rotation speed. These ideas have not found wide acceptance in the peer-reviewed literature, but are discussed in the corridors of conferences and online forums, whispered as possibilities that the mainstream community has yet to refute to everyone's satisfaction. But the comet, that's where the real mystery lies. The three-eyed atlas got its name as the third confirmed interstellar object that was recorded passing through our solar system. The first was Oumuamua in 2017, a strange elongated body that passed through the inner solar system and exhibited acceleration that could not be fully explained by ordinary cometary evaporation. The second object was a comet in 2019, which looked and behaved more like the comets we know, a reliable ball of ice and dust, following predictable physical laws. The three-eyed atlas was discovered in the year 2025 and tracked as it fell towards the sun on a hyperbolic orbit, moving too fast to be caught by the gravity of our star, clearly a visitor just passing by on its way back to interstellar space. These objects are incredibly valuable to science. They are the only samples of materials from other star systems, at least until we develop technologies to send probes to the nearest stars and return with physical samples, which is unlikely to happen in any of our lifetimes. Each photon of light we collect from the interstellar comet carries information about chemistry, the composition of protoplanetary disks around other suns, and whether the processes that formed our solar system are universal or unique. When the three-eyed atlas disappeared behind the sun, we lost the ability to collect this data, at least for a while. The question now troubling astronomers is simpler and more disturbing than any speculations about solar winds or earthquakes. When the three-eyed atlas appears again after disappearing behind the sun, if it ever does, will we be able to recognize it? Has the sun consumed our interstellar guest? Could the intense heat, radiation, and magnetic disturbances near our star have altered it, destroyed it, or completely evaporated it? We will soon find out, and the answer may overturn all our notions about these alien travelers. Part 2. The Traveler We Lost. The story of the three-eyed atlas begins, like most comet discoveries, with patience, with automated telescopes scanning the sky each night in search of something moving against the backdrop of stars. The Atlas Observatory, short for the Asteroid Collision Warning System, consists of 4 robotic telescopes located around the world and was primarily created to detect asteroids that may pose a threat to Earth. But telescopes make no distinctions. They capture everything that moves, including comets, and in the early months of 2025, they recorded something extraordinary. The object initially appeared as a faint streak in images from Hawaiian stations. Subsequent observations from other observatories confirmed that it was moving quickly. Trajectory calculations showed the characteristic sign of a hyperbolic orbit with an eccentricity greater than 1, indicating that this object was not bound to the sun. He came from somewhere else, and after a close approach to our star, he will leave us, heading back into the cosmic ocean between the stars. The orbital energy of the comet proved incorrect for an object from the solar system. It was an interstellar object, and the astronomical community quickly reacted. Telescope time, which had always been in short supply and was highly contested, became available within days. Spectroscopy, the analysis of light reflected or emitted by a comet, became a priority task. What was this object made of? Did it contain the same mixture of water ice, carbon dioxide, and organic molecules typical of comets formed in our solar system? Or its composition indicated alien chemistry, the ratio of elements suggesting conditions formed around a different type of star? The initial data caused confusion. The brightness of the comet Three-Eyed Atlas did not meet astronomers' expectations. Comets usually become brighter as they approach the sun, following a predictable curve associated with increased sublimation of ice as solar heat intensifies. The water ice begins to sublimate, turning directly from solid to gas as sunlight heats the surface to about 200 Kelvin. Other volatile substances, such as carbon monoxide and carbon dioxide, sublimate at even lower temperatures, creating activity at significantly greater distances from the sun. The brightness of the Three-Eyed Atlas displayed alignment periods when the comet did not become as bright as predicted by models, followed by sharp spikes in light indicating discrete emissions of dust or gas. The coma, a blurred cloud of gas and dust surrounding the comet's core, appeared unusually dim in some observations. The dust production seemed lower than expected for a comet of this size. Some researchers suggested that the core may have an unusually high density, composed more of rock than ice, which could explain the weak activity. Others expressed the opposite opinion, suggesting that the core was extremely porous, almost like a pile of stones held by weak gravity, and that such a structure caused the sublimation of ice in unpredictable bursts rather than gradually. Additionally, there were non-gravitational forces. Comets do not follow purely capillary orbits determined solely by the sun's gravity. When ice sublimates from the nucleus, it creates gas jets that act like tiny rocket engines, slightly deviating the comet from its predicted path. These non-gravitational accelerations are small but measurable, adding uncertainty to predictions about where exactly the comet will be at any given moment. For the three-eyed atlas, these deviations were particularly challenging to model. The orbital calculations were constantly refined, the errors changed, and the astronomers became increasingly uncertain about when and where the comet would reappear from behind the sun. Some observations hinted at possible destruction before its disappearance. The cores of comets are fragile formations, loosely bound collections of ice and rock that can shatter under thermal stress or tidal forces. When a comet breaks apart, it often forms a trail of smaller fragments moving along similar orbits, which can sometimes be seen as several condensations in the coma. Images of Comet 3 and Atlas showed possible asymmetries and elongations, which could indicate that the core is starting to break apart. If the comet had fragmented before it disappeared, the question becomes even more relevant. What emerges from the sunlight may not be a single object, but a stream of debris. Or perhaps nothing will remain if the fragments become too small to detect. The comparison with previous interstellar visitors was inevitable. The object Oumuamua, which was first discovered as interstellar, was not confirmed as a comet. It showed no visible coma, had no dust tail, nothing that could definitively identify it as an icy body. Yet it accelerated away from the sun in a way that could not be explained by gravitational forces alone. The most likely explanation remained that it was gas emissions from a comet, but with more exotic volatile compounds than water, possibly carbon monoxide or molecular nitrogen, substances that sublimate without forming visible dust. Alternative explanations, from solar sails to alien probes, captivated the public imagination, but found no support among scientists working with evidence rather than speculation. Comet 2 and Brusov behaved more typically, with a distinct coma and tail, as well as brightness changes that reasonably matched standard comet models. Its spectrum showed the presence of water vapor and carbon monoxide, chemistry similar to what we observe in solar system comets. In a sense, this was encouraging, as it indicated that the process of planet formation around other stars follows similar laws and creates analogous objects. However, Brusov also showed signs of fragmentation near perihelion, its closest approach to the sun. The images captured what seemed like a small fragment breaking away from the main core, reminding that these interstellar travelers do not always survive their passage through the inner solar system. Now 3, and Atlas followed a similar path, heading towards the sun, and we lost sight of him at the most inopportune moment. The geometry of a solar conjunction, when an object is positioned behind the sun relative to Earth, creates an observational gap that can last for days or weeks, depending on the trajectory and brightness of the object. For the dim comet, already showing unusual behavior, this rupture becomes a black box, a period when anything can happen, and we will have no way to know. The comet could break apart, it could shine brightly, it could remain intact and simply be too close to the sunlight to be visible. We won't know until it appears, if it ever does. Models attempted to predict what would happen based on the assumed sizes and compositions of the cores. If the core was large and mostly rocky, thermal models suggested it would survive with minimal mass loss. If the object were small and icy, the heat near perihelion could completely vaporize it, leaving only a growing cloud of gas and dust. The uncertainty in the dimensions of the nuclear object was colossal, ranging from several hundred meters to several kilometers, 10 times or more, and this uncertainty reflected on all forecasting models, turning predictions into guesses. Astronomers used the phrase invisible interstellar traveler, somewhere beyond the solar glare, hidden from all telescopes ever created by humanity. An object from another star system either survived or perished, and we could only wait and speculate what would appear when the geometry of observation became possible again. This waiting felt like an eternity compressed into days. Part 3. When the solar wind meets alien ice. The sun is not such a harmless creature. We perceive it as our kind star, giving life and warm light, making Earth habitable. But up close, it turns out to be a cruel and chaotic, bubbling sphere of plasma, where temperatures reach millions of degrees, and magnetic fields twist into configurations that store energy like compressed springs. When these springs snap, the consequences can be catastrophic for everything nearby. The coronal hole that opened in October 2025 was one of those events that made solar physicists anxious. Coronal holes are areas where the sun's magnetic field opens into space instead of looping back to the surface. These open magnetic lines act as highways for solar wind, allowing high-speed plasma to burst into the solar system. The normal speed of solar wind is about 400 kilometers per second. The wind bursting from this particular coronal hole was moving at 700 kilometers per second, almost twice as fast, carrying more momentum, energy, and potential destruction. When solar wind of such speed collides with a comet, the interaction becomes complex and turbulent. Comets are not protected by a magnetic field like Earth. They have no magnetosphere to deflect charged particles. Instead, the solar wind collides directly with the coma, a cloud of gas and dust surrounding the nucleus, and strange physical laws begin to act. The gas in the coma is ionized by the sun's ultraviolet radiation, creating a population of electrically charged molecules. These ions react to magnetic fields, and the solar wind carries frozen magnetic lines that wrap around the comet like a cloak. As a result, a magnetic tail is formed, a structure created by the interaction of the solar wind's magnetic field and the comet's ionized gas. This tail can stretch millions of kilometers downstream, away from the sun, dimly glowing in the light of ionized carbon monoxide and other molecules. The tail is not a passive structure. Turbulence in the solar wind causes the tail to sway and flutter. Disconnections can occur, where the tail completely detaches and a new one begins to form. These interactions can be observed from Earth using appropriate instruments, providing clues about the state of the solar wind and the gas formation speed of the comet. But what happens when a comet collides with a particularly strong solar wind while being subjected to intense solar heating near perihelion? The story provides several frightening examples. A comet discovered in 2012, predicted to be spectacularly bright, disintegrated during its close pass by the sun in 2013. Images from solar observatories showed a comet entering perihelion as a bright object and emerging as a cloud of dust. The core appeared to have completely shattered, unable to withstand thermal and tidal stresses. Comet Lovejoy, which passed within 140,000 kilometers of the sun's surface in 2011, somehow survived despite predictions of its destruction. The images capture the tail of a comet stretching millions of kilometers after perihelion, fueled by powerful gas emissions from its overheated core. Lovejoy's survival was a surprise, and still lacks a complete explanation. A certain combination of core size, composition, and structural strength allowed it to withstand the heating that should have completely vaporized it. The comet Tri-I Atlas did not pass as close to the sun as those extreme comets, but it entered the region where solar influence becomes dominant, doing so during a period of unusually intense solar wind. The question was whether the combination of factors, thermal stress, radiation heating, solar wind pressure, and possible prior destruction, would be enough to destroy it. Some researchers proposed more exotic interactions. The model of an electric comet, promoted by a small group of plasma physicists, suggests that comets accumulate electric charges when interacting with solar wind, and that electric forces, rather than just thermal sublimation, drive comet activity. Mainstream astronomy did not accept this model, believing that traditional physics adequately explains observations without resorting to electrical effects. However, supporters point to phenomena such as comet tail disconnections and sudden brightness changes as evidence that electrical processes play a role. The hypothesis goes even further into the realm of alternative theories, suggesting that strong solar wind events can cause charge separation in a comet's coma, which, under certain circumstances, may lead to explosive disruptions or trajectory changes exceeding those expected from a simple gas ejection. The evidence for these claims is disputed. The theoretical foundation is incomplete, but ideas continue to circulate as they attempt to explain observations that do not quite fit standard models. When Tri-I Atlas disappeared during a major solar storm event, supporters of electric comet models saw this as potential confirmation of their ideas. Mainstream astronomers viewed it as an unfortunate accident, but ultimately a coincidence of events. The uncertainty of the situation lies in the fact that we do not actually know what Comet Tri-I Atlas is made of. Spectroscopic observations before its disappearance were limited and did not provide a complete spectrum of its composition. It may primarily consist of water ice, like many comets in the solar system, or it could be rich in carbon monoxide, which evaporates at much lower temperatures and can cause activity at great distances from the Sun. It is also possible that its composition is rich in silicates and poor in volatile substances, making it more like an asteroid than a typical comet. Each of these states will react differently to solar heat and interaction with the solar wind. If the core of the comet is extremely porous, almost like aerogel with a density just above that of the gas in the coma, thermal waves will penetrate deeply, heating the subsurface ice, and possibly causing complete structural destruction due to a cascade of sublimation. If the core is covered with a layer of dust insulation, gas formation will be concentrated in several active areas, creating jets that can spin the core or uncontrollably change its rotation. If the core is a contact binary made up of two lobes connected by weak gravity, tidal forces and thermal stress can tear it apart. In this scenario, the Sun acts as a cosmic guardian, a destructive force testing every object passing through the inner solar system. Interstellar comets, formed under various conditions and possibly with different structural properties compared to the comets of the solar system, may be particularly vulnerable or, conversely, more resilient, hardened by the conditions that made them more durable. We will not know until we see what happens. A comparison with the Shoemaker-Levy 9 comet is useful. This comet was torn apart by tidal forces during a close pass by Jupiter in 1992. It broke into more than 20 fragments, which later struck the planet in a spectacular series of impacts. The destruction occurred because Jupiter's gravitational gradient across the diameter of the comet exceeded its own self-gravity, literally tearing it apart. The tidal forces of the Sun are much weaker at the distance where the Comet Tri-I Atlas passed, but the comet, already weakened by thermal stress or previous destructions, may succumb to forces that a healthy core would easily withstand. Does this mean that the Sun has revealed something frightening about interstellar visitors? The answer depends on what we will see when the comet emerges from the conjunction. If 3 and Atlas appear whole, continuing their hyperbolic path with normal gas formation and dust creation, then the event with the solar wind will merely be a footnote, an accident that sparked speculation, but ultimately means nothing. If the comet has broken apart or disappeared, we face troubling questions about whether interstellar objects are inherently more fragile than our models suggest, and if there is something in their formation or structure that makes them vulnerable to solar effects in ways we did not foresee. Astronomers mark dates in calendars, check ephemerides, and prepare observation plans in anticipation of the moment when the Tri-I Atlas comet will be visible again. The timeline depends on several factors, including the exact trajectory of the comet, which remains uncertain due to non-gravitational forces, its brightness, which could vary significantly, and the observation geometry that determines how far from the Sun the comet must be for telescopes to capture it against the sky. Current forecasts suggest that the comet is expected to appear after the solar conjunction at the end of October or early November 2025, reaching sufficient solar distance and angular separation from the Sun as seen from Earth. For observation using specialized equipment, the first detection attempts will likely be made with space observatories that can more effectively block sunlight than ground telescopes. SOHO, the Solar and Heliospheric Observatory, is equipped with coronagraphs designed to create artificial eclipses, allowing observation of areas close to the Sun where comets often hide. A stereo observatory of solar-terrestrial relations consisting of 2 spacecraft in solar orbit provides various angles to capture a comet earlier than ground observations. The Parker Solar Probe, humanity's closest spacecraft to the Sun, follows an orbit that periodically brings it near Mercury's orbit, through regions where the speed and temperature of solar wind reach extreme values. If the probe's trajectory approaches Tri-I Atlas during the conjunction, its instruments may capture data about the comet under conditions inaccessible to ground-based telescopes. However, Parker's scientific tasks focus on the solar corona and solar wind, not comets, and if a comet does not fall within the probe's narrow field of view at the right moment, data from this critical period will be lost. The mission scientists did not announce any successful encounters, which may indicate that the geometry did not align, or that the comet was too dim for the Parker instruments to detect against the bright solar background. What images of the restored object will be the first? At best, the comet will appear as expected, perhaps a little dimmer due to dust loss, but otherwise intact, with a visible coma and tail indicating active sublimation of ice from the nucleus. Spectral analysis will reveal familiar lines of water vapor, cyanogen, and carbon monoxide, molecular fingerprints confirming the composition of the comet. The length and structure of the tail will provide information on gas production rate and solar wind conditions during the post-connection period. Astronomers will measure the brightness, compare it to previous values, and assess whether the comet has lost significant mass during its closest approach to the Sun. In the worst case, nothing will appear. The sky will remain empty where Tri-I Atlas should be, indicating its complete destruction. The comet's core could have shattered into pieces too small to be detected individually, or completely evaporated, leaving only a dissipating cloud of gas that is too sparse to appear as a distinct object. This would be a disappointing outcome from a scientific perspective, but not unprecedented. Several comets have disappeared after close approaches to the Sun, and their loss has become an important part of our knowledge about the physics of comet fragmentation. Between these extremes, there are numerous possibilities. The comet may return in the form of several fragments, forming a chain of condensations along its orbit, indicating that the core has shattered, but its parts remain. Streams of fragments are difficult to observe, as each individual part is dimmer than the original core, but they provide valuable information about the structure of the core and the mechanisms of destruction. If the comet Tri-I Atlas returns in fragments, analysts will be able to measure the distances between them and their speeds to reconstruct when and how the destruction occurred. Another possibility is a state of inactivity. The comet may have exhausted its near-surface volatile substances during its close passage to the Sun, leaving a darkened crust that will prevent further sublimation until solar heat cracks the crust or erosion exposes fresh ice. Sleeping comets look like asteroids, lacking a coma or tail, just bare rock reflecting sunlight. If Tri-I and Atlas become inactive, we will lose the ability to study their gas composition, but gain information about surface processes and the formation of insulating shells. The most intriguing scenario involves an unexpected increase in brightness. Sometimes comets fragment in such a way that fresh, volatile, rich materials become exposed to sunlight, causing a sharp increase in gas production and brightness. A disintegrating core can create new, active regions, increasing the overall sublimation surface. If Tri and Atlas fragment and simultaneously become brighter, the comet that appears may be more impressive than the one that vanished. Although in a fragmented state, it will likely dim quickly as small pieces exhaust their ice supplies. Spectral diagnostics will be crucial. Observations before the connection showed typical signatures of water and possibly carbon monoxide, but a complete spectral analysis was never obtained. Spectroscopy after the connection can reveal substances that were not previously detected, either because the comet did not produce them in significant amounts or because we were not looking at the right wavelengths. Emission lines of oxygen will indicate the sublimation of water. Cyanide, indicates carbon-nitrogen chemistry. Sodium and iron lines sometimes appear in comets and may indicate the unearthing of metal-rich materials from the inner core. Astronomy enthusiasts can play an important role in recovery efforts. A network of home telescopes distributed around the world provides continuous sky monitoring, which professional observatories with limited observation time and scheduled programs cannot offer. If the comet Tri-I Atlas unexpectedly breaks into many separate fragments, amateur observers may be the first to notice it. Amateur astronomy is becoming increasingly significant as digital cameras and software enable enthusiastic astronomers to create observations comparable in quality to those of professionals. In real time, the mystery of space unfolds, and anyone with a telescope and a clear sky can participate. A comet may reappear at any moment if it has survived, or days may pass, then weeks, before astronomers reluctantly conclude that Tri-I Atlas has vanished. Consumed by sunlight, she came from afar. This uncertainty is both tormenting and exhilarating. We did not send a probe to intercept the comet. We have no way to actively search for it, other than to aim our telescopes at the predicted spot and wait. All we can do is watch, wonder, and prepare for what will emerge from the sunlight. A broader question torments the astronomical community. If the comet's core has vanished, do we still have Tri-I Atlas? Or is it just debris? A scattered cloud of dust and gas that once was an interstellar comet, but now does not qualify as a separate object. From a philosophical standpoint, This resonates with the paradox of the ship of Theseus. If over time every board of a wooden ship is replaced, is it still the same ship? If a comet breaks into 1,000 pieces, each moving almost in the same orbit, carrying material away from the original core, are they still together a comet? Or has the comet ceased to exist? There is no formal definition that answers this question. It is a matter of agreement and convenience, and different researchers will respond differently depending on their perspective. But this question is important because the Tri-Eye Atlas represents something valuable and irreplaceable, a specimen of another star system, and its loss is felt as something more than just the loss of an astronomical target. It feels like a loss of connection with something vast and distant, the threads linking us to a broader galaxy severed before we could fully grasp what we held. Why does all this matter beyond the narrow confines of planetary science journals and astronomical conferences? Because people are beings seeking patterns, evolved to find meaning in correlations, seeing connections even when they are not there. The simultaneous occurrence of a significant solar event, the disappearance of an interstellar comet, and several major earthquakes on Earth activated all signals in our collective subconscious that scream something is happening. The main scientific position regarding the connection between solar activity and earthquakes is clear and unequivocal. Earthquakes are caused by plate tectonics, the slow and steady movement of lithospheric plates gliding over convecting mantle, the accumulated energy of stress in the crust that ultimately exceeds the resisting forces keeping the faults locked. Solar activity lacks a plausible mechanism to cause this phenomenon. Magnetic fields do not affect rocks. Solar wind particles do not penetrate the Earth's surface. They are stopped by the magnetosphere and atmosphere. The thermal energy supplied by solar radiation is negligible compared to the Earth's internal heat. Each study of earthquake catalogs aimed at finding correlations with solar cycles or specific solar events has found nothing but random coincidences. Nonetheless, correlations continue to emerge in datasets, creating intriguing patterns that do not reach statistical significance, but do not vanish either. Some researchers, operating on the edge of acceptability, continue to explore possible mechanisms. Can ionospheric disturbances caused by solar activity affect the electrical properties of fault zones? Can minor changes in the Earth's rotation speed or magnetic field orientation, caused by solar wind momentum transfer, modulate tectonic stress at levels too small for direct measurement but sufficient to trigger a fault that is already close to rupture? Can there exist a magneto-hydrodynamic connection between the ionosphere and the conductive layers in the crust, transmitting energy in ways we do not yet understand? These ideas face enormous skepticism, as extraordinary claims require extraordinary evidence, and the existing evidence remains, at best, indirect. However, the human mind does not operate on thresholds of statistical significance. He works based on narratives, on stories that connect disparate events into a whole. When the sun attacks, earthquakes occur, and a comet disappears in the same news cycle, the narrative forms itself, even if physics does not support it. The interstellar nature of the Three-Eye Atlas comet adds another layer of mystery and speculation. These objects come from beyond our solar system, from realms we can barely imagine. Formed from materials whose composition and isotopic ratios may differ from the norms of the solar system, they are literally alien, in the truest sense of the word. Humanity has always projected its hopes and fears onto the strange and unknown. When Oumuamua exhibited acceleration that could not be immediately explained by normal cometary gas ejection processes, speculation began about its artificial origin, alien probes conducting reconnaissance, and technologies beyond our understanding. The simplest explanation remained within natural processes, but the hypothesis of an alien probe captured the public imagination, as it fulfilled narrative needs that dry scientific articles on carbon monoxide sublimation could never address. The disappearance of the Three-Eyed Atlas during a solar storm raises similar speculations. Did the comet carry something, encode something that made it a target? Are we witnessing a cosmic quarantine protocol? Does the sun eliminate potential threats from interstellar space before they can penetrate the inner solar system? The scientific absurdity of these ideas does not diminish their psychological appeal. We strive for the universe to hold mysteries deeper than orbital mechanics and spectroscopy. We yearn for hidden meanings behind celestial alignments. We want comets to be not just dirty snowballs, but messengers carrying information, life, or meaning. The panspermia hypothesis, the idea that life spreads through space on comets and asteroids, gives these desires a scientific veneer. If comets brought organic precursors that led to life on Earth during the intense bombardment billions of years ago, then each comet becomes a potential carrier of seeds, and interstellar comets are especially valuable as they may carry chemistry from the biospheres around other stars. The destruction of the 31st Atlas, if it indeed happened, becomes the destruction of a biological sample, a library burned before we could read its contents. More exotic possibilities are discussed in marginal communities. Adherents of the electric universe view the interaction of the sun with a comet as proof of plasma physics, claiming that mainstream science ignores it. They point to unusual changes in the brightness of the comet, to the strong solar wind, to events of disconnection in other comet tails, and assert that these phenomena require electrical rather than gravitational and thermal explanations. The mathematics of their models rarely withstands criticism, and predictions often do not match observations, but the intuitive appeal of electricity as a universal force and the visual drama of lightning and sparks give the ideas of an electric universe a resilience that surpasses their scientific shortcomings. Inevitably, a conspiracy theory arises. Our space agents are hiding data about the Parker Solar Probe's close approaches to the Sun. Did the instruments capture images or spectra of the 31st Atlas during the conjunction that officials decided not to publish? What could motivate such secrecy? Perhaps the comet exhibited behavior that could not be explained, challenging fundamental assumptions and frightening those who understood the consequences. Perhaps it was destroyed in a way that nature does not predict, or emitted signals, or changed its trajectory in a way that indicated control. These scenarios are extremely unlikely, almost impossible, but the absence of evidence becomes proof of a conspiracy for a mind predisposed to distrust official narratives. The psychological function of conspiracy theories is well studied. They provide control or the illusion of control in the face of random and chaotic events. They replace a universe of meaningless coincidence with a universe of hidden order and meaning, even if that meaning is sinister. It is better to believe in conspiracies than to accept that earthquakes happen by chance, that comets break apart for no reason, that we are tiny sparks of consciousness on a fragile world, drifting through an indifferent cosmos. A narrative about hidden knowledge and suppressed truths evokes more emotions than a tale of patient scientific research slowly approaching justified conclusions. But here's the thing. Sometimes the universe aligns in a way that defies probability. Sometimes a coincidence turns out to be too perfect, even if we cannot establish causal connections. The events that occurred in October 2025, a solar storm, the disappearance of a comet, and earthquakes could be such a coincidence, so unlikely that it demands our attention, even if it ultimately holds no significance. This could be the first hint of connections we do not yet understand, weak links between geophysical systems and space weather, operating at levels below our current thresholds of detection. Science moves forward by exploring anomalies rather than dismissing them. Researchers studying the correlations between solar storms and earthquakes are engaged in a legitimate, albeit speculative, science. They are unlikely to find anything, but the search process itself matters. When the comet Tri-X Atlas emerges from behind the sun, if it does, we may not recognize it. The comet that entered may not be the one that exits, and when astronomers publish their analyses of the observed, they will present explanations based on physics, chemistry, and orbital mechanics. Some will accept these explanations and move on. Others will continue to seek hidden meanings, connections between the comet and earthquakes, as well as solar storms that transcend material causality. Both of these responses are human. Both reflect a deep need to contemplate our place in the cosmos, which offers more questions than answers. The sun has done something terrible. A comet has vanished. The earth trembled, and whatever truth we seek, these events have left us with equal feelings of wonder and anxiety. Part 6. The comet that we can see. While Tri-X Atlas plays hide and seek behind the sun, another comet puts on a show that you can truly observe if you know where to look and are willing to wake up before dawn or stay up late into the night. Comet C 2025 A6, discovered by the Mount Lemmon Observatory in Arizona and named Lemmon, approaches a close encounter with the sun, reaching brightness levels that make it visible in binoculars or small telescopes, possibly even to the naked eye for observers in dark conditions away from light pollution. The next 2 weeks represent the optimal period for observations. The perihelion of Lemmon, its closest approach to the sun, is scheduled for mid-November, 2025. However, the geometry of its orbit allows the comet to be seen from Earth at maximum visibility just before perihelion, when it is still far enough from the brightness of the sun for comfortable observation. Currently, the comet can be seen in the eastern sky before dawn, rising several hours before the sun, shining with a soft blurred light typical of an active comet with a well-developed coma and possibly a short tail. The predicted brightness of the Lemmon comet currently fluctuates between the 4th and 5th magnitudes, which is at the edge of visibility to the naked eye. The human eye can usually distinguish objects up to the 6th brightness class under good conditions, and a 4th class comet should be easily visible away from city lights, but to locate it accurately without binoculars, one must know exactly where to look. At this moment, the comet is moving through the constellation Cancer, heading east against a backdrop of stars, while online observation maps show its path relative to well-known star patterns. Observing comets requires patience and a dark sky. Unlike planets, which appear as clear points or disks, comets are blurred objects whose light is scattered over a large area. This blurriness makes them more sensitive to light pollution and sky conditions compared to compact objects of similar brightness. A 4th-class comet can completely disappear against a bright suburban sky, where 4th-class stars remain easily distinguishable. To observe successfully, one must travel far from urban areas to places where the Milky Way is visible overhead, as the darkness of the sky allows the eyes to distinguish objects with low surface brightness. Binoculars are the ideal tool for observing comets. They provide sufficient magnification to focus the light of the comet while maintaining a wide field of view, making it easier to locate and track it. Binoculars with 7 by 50 magnification, favored by many astronomy and nature enthusiasts, are especially good for these purposes. If possible, mount them on a tripod to avoid handshaking and prolong observation without fatigue. The comet will appear as a small blurred spot, clearly not a star, possibly with a hint of green due to the diatomic carbon molecules in its coma. Telescopes can reveal more details, showing the structure of the coma, any jets or fans of material emanating from active regions on the nucleus, as well as the tail, if it has formed sufficiently. However, higher magnification narrows the field of view, making the initial sighting of the comet more difficult and harder to keep it centered while the Earth rotates. Many experienced comet observers prefer binoculars for aesthetic reasons. A wide field of view allows the comet to be seen in the context of the starry Milky Way, highlighting its nature as a temporary visitor moving through more permanent celestial landscapes. The first observations of Comet Lemmon revealed something that both excites and alarms comet scientists. The brightness of the comet did not match the predicted models. Comets are notoriously difficult to predict, as their brightness depends on factors we cannot measure directly, such as nuclear size, composition, rotation state, surface, and the ratio of dust to gas. Models base their assumptions on these parameters, relying on the statistics of other comets, but individual comets often deviate from average behavior. The Lemmon comet displayed phases where its brightness increased faster than expected, followed by plateaus where the brightness remained nearly constant despite the decreasing distance to the sun. These deviations may indicate several phenomena. Burst activity, when the sudden release of fresh volatile substances leads to a temporary increase in gas and dust production, can cause a rapid increase in brightness. The rotation of the core, where different hemispheres are exposed to the sun, creates periodic fluctuations in brightness if one is more active. Or, more alarmingly, these deviations may signal the early stages of fragmentation, when the core begins to crack under thermal or tidal stresses. Fragmentation is a hidden threat that haunts every prediction about comets. A comet can shine brightly as it follows its expected trajectory to perihelion, appearing healthy from all sides, and then suddenly start to break apart. This process can be both fast and gradual. Sometimes a large chunk breaks off and forms a separate condensation, noticeable next to the main core. In some cases, the entire core disintegrates into a cloud of small fragments that are individually too dim to see, but together can create a sharp increase in overall brightness as their combined surface contributes to enhanced sublimation. The physics of fragmentation involves mechanical strength, thermal loads, and rotational state. Comet nuclei are weak structures, more like compacted snow than solid rock, held together mainly by their weak gravity, supplemented by the strength from ice sintering and possibly organic resins. When the sun heats one side of the core, thermal expansion creates tension, If the core rotates, centrifugal forces add mechanical stress, while jets of gas create flows that can increase the core's rotation speed. At some point, the accumulated tension exceeds the material's strength. Cracks begin to spread, and the core disintegrates. Lemmon's science of sublimation adds another layer of complexity. It seems that the comet is moving under the influence of the sublimation of carbon monoxide or carbon dioxide, no less than that of water sublimation. These molecules are more volatile than water, meaning they transition from solid to gas at lower temperatures and greater distances from the sun. A comet, propelled by carbon monoxide, can remain active far beyond the snowline, where water ice stays frozen, forming a cometary shell and tail while still in the distant part of the solar system. As the comet approaches perihelion and the temperature rises, the sublimation of water ultimately begins to dominate, often causing a shift in activity patterns and brightness behavior. The interaction of the tail with the solar wind provides another opportunity for observation. The ion tail of a comet, if it forms, will point directly away from the sun, blown by the solar wind like a flag in the breeze. The dust tail follows a curved path, with particles moving under the influence of solar radiation pressure while maintaining their orbital motion from when they were released from the nucleus. These two types of tails, the ion tail and the dust tail, often form distinctive structures visible in photographs. The ion tail appears bluish due to the emission of carbon monoxide ions, is straight, and sometimes includes streams and knots caused by irregularities in the magnetic field of the solar wind. The dust tail has a yellowish-white color from reflected sunlight, wider and more diffuse, gently curving away from the comet's nucleus. The comparison of Lemmon and the three-eyed Atlas comet highlights the main differences between comets born in the solar system and interstellar visitors. Lemmon formed 460 million years ago in a gas and dust disk surrounding the young sun, likely in the region beyond Neptune, where temperatures were low enough for water and other volatile substances to condense into ice. Gravitational disturbances from giant planets eventually propelled it into the Oort cloud, a vast spherical reservoir of comets surrounding the solar system at a distance of up to 100,000 astronomical units. Something, possibly the gravitational influence of a passing star or a giant molecular cloud, disrupted the orbit of Lemmon, sending it back towards the sun on the path we are now observing. Its composition reflects the primordial chemistry of the solar system. Isotopic ratios and molecular abundances existed in our local region of the galaxy 4.5 billion years ago. The three-eyed Atlas comet formed elsewhere, around another star, under conditions that could have been both similar and radically different. The temperature and pressure in this protoplanetary disk, the amount of heavy elements, the radiation environment, and the time of planet formation, all these factors influence the composition and structure of comets. Comparing interstellar comets with comets from the solar system, we are essentially comparing samples from different stellar nurseries, seeking common traits that reveal universal processes and differences that highlight local variations. A lemon serves as a reminder of how fragile comets are. Each comet is a risk of disintegration. Most survive after perihelion, losing some mass due to sublimation, retreating to the distant regions of the solar system or beyond, and remain intact. Some comets fragment, creating spectacular displays with multiple nuclei and expanding clouds of dust that glow brightly and fade. Some disappear completely, destroyed so thoroughly that tracking them afterward becomes impossible. Observing the Lemmon at its peak visibility is not just an opportunity to enjoy a beautiful celestial spectacle. This is a chance to witness a surviving object that has endured billions of years in the cold of the Oort cloud and is now undergoing trials from solar heat and radiation that could lead to its destruction. The circumstances have aligned favorably. While the three-eyed Atlas is hidden behind the sun, Lemmon becomes an alternative target, another comet that we can observe and explore. If you have never seen a comet with your own eyes, only encountered them in images on screens or diagrams in textbooks, you now have a chance to correct that. Go outside before dawn, find a dark place, allow your eyes to adjust for 10 to 15 minutes, and observe the eastern part of the sky in the constellation Cancer. This blurry spot of light, if you find it, contains ice formed before the Earth appeared, organic molecules predating life, and silicate dust older than our planet. You observe a messenger from the dawn of the solar system, and in just 2 weeks it will vanish from sight, its brief moment of visibility will end, and its fate, survival or decay, remains unwritten. Look at the sky now, while Atlas hides. Part 7. The Swan and Context. Comets usually appear in groups, or at least it seems so when we track these icy visitors. In reality, the situation is more prosaic. At any time, many comets orbit around the Sun at various distances, most of which are too dim to be observed without large telescopes, while some are bright enough to attract the attention of astronomy enthusiasts, and very rarely one becomes impressive enough to be visible to the naked eye and enter public consciousness. The clusters we perceive are the result of observational bias and the statistical nature of comet discoveries, yet they still create periods when comet observers have several objects to choose from. The year 2025 promises to be one of those periods, alongside Comet Lemmon in 3 and the Atlas. Another comet, designated as C2025 R2 Swan, has entered the catalog. The Swan refers to the instrument of solar wind and isotropy installed on the spacecraft SOCOD, which observes the sky in ultraviolet wavelengths sensitive to hydrogen emission. Comets produce huge clouds of hydrogen, neutral hydrogen atoms formed when water molecules break apart under the influence of solar ultraviolet light. These clouds are invisible to optical telescopes but brightly glow in certain ultraviolet ranges, and the Swan can detect them from great distances, sometimes spotting comets months before they become visible to ground observers. In 2025, the Swan was discovered due to its hydrogen crown, a vast invisible cloud surrounding the visible comet. Subsequent optical observations confirmed the discovery and allowed for trajectory calculations. The comet moves along an elongated elliptical orbit that will bring it to perihelion in early 26th year of the 2000s, occurring significantly later than the close approach of Comet Lemmon, but soon enough to maintain interest among comet watchers preparing their equipment and observation plans. Initial brightness estimates of the Swan suggest it may reach the 6th or 7th magnitude at perihelion, making it a target for binoculars, but likely not visible to the naked eye except under special circumstances. The predicted brightness depends on assumptions about the size of the nucleus and the level of activity, both of which remain uncertain. Some comets discovered by Lebedev exceeded expectations, becoming significantly brighter as they approached the Sun. Others disappointed, remaining dull and blurry despite hopeful forecasts. The only way to know is to observe and wait. One of the interesting possibilities related to new comets is meteor showers. When a comet approaches the Sun, it ejects dust that spreads along its orbital path, creating a stream of particles. If Earth's orbit intersects this stream of dust, high-speed particles, usually between 30 and 70 kilometers per second, collide with our atmosphere and vaporize, creating bright trails that we call meteors or shooting stars. Most meteor showers we observe annually, such as the Perseids in August or the Geminids in December, occur because Earth passes through well-known dusty trails left by comets that have made many perihelion passes and deposited dust over centuries or millennia. New comets, making their first pass through the inner solar system, can cause unpredictable meteor activity. The distribution of dust along the orbit has not yet smoothed out from multiple passes and gravitational disturbances. Fresh ejections can create dense clusters of particles. If the Earth accidentally passes through one of these clusters, the number of meteors may sharply increase, creating a meteor storm with hundreds or thousands of visible meteors per hour. These events are rare and difficult to predict, as they depend on the precise spatial distribution of dust, which we cannot measure directly. The orbit of Comet Swan will be precisely calculated in the coming months, and astronomers will determine if there are possible intersections with dust streams that could reach Earth. Even a low probability of a meteor shower excites comet and meteor enthusiasts. Observing a meteor storm is an experience worth having, a celestial fireworks show that occurs perhaps once or twice in a generation. Meteors radiate from a point in the sky called the radiant, where parallel trajectories of particles enter the atmosphere. During the storm, the entire sky looks as if it is enveloped in meteors. Glowing streaks appear in all directions, overwhelming perception in a way that photographs can never convey. But for every comet that shines brightly and meets expectations, there are several others that do not fulfill hopes. The history of comet astronomy is full of failed predictions, where objects expected to become great comets remained weak and unnoticed. The Comet comet was predicted in 1973 to be one of the brightest comets of the century, but as it barely became visible to the naked eye, it disappointed millions who were expecting a spectacular show. The Osan comet was supposed to survive perihelion and shine brightly in 2013, but instead, it broke apart. These failures teach humility. and remind us of how much we still do not understand about the physics of comets. The comparison of the brightness curves of comets Swan and Lemmon will ultimately provide useful scientific data. Observing both comets simultaneously under similar solar conditions will allow for a direct comparison of activity levels and sublimation physics. Differences in brightness of objects at comparable distances from the Sun indicate variations in the size of nuclei, composition, or surface properties of comets. If one comet is primarily made of water and another of carbon monoxide, their activities will differ in characteristic ways. If one comet breaks apart while another does not, it gives us clues about the structural differences that determine vulnerability to fragmentation. Using Swan and Lemmon as contrasting examples creates tension in the narrative. Many comets fail. Will the Comet 3 and Atlas be the same? Is there something in the current solar environment that makes the survival of comets less likely? The coronal event surge in October 2025 could have been a random occurrence, or it may signal a period of heightened solar activity that threatens any comet passing through the inner solar system. The 11-year solar activity cycle is approaching solar maximum when sunspots and coronal ejections become frequent and solar wind speeds and magnetic fields increase. Comets approaching perihelion during solar maximum face harsher conditions than those arriving during solar minimum. The story of comet fragmentation provides alarming statistics. The Shoemaker-Levy 9 comet was destroyed by Jupiter in 1992, leading to impressive collisions in 1994, demonstrating how completely a comet can be obliterated by gravitational and tidal forces. Comet 73 Pa Schwarzmann-Wachmann 3 broke apart during its appearance in 1995, splitting into many fragments that dispersed over the following years. By the time of its return in 2011, the comet had already broken into over 60 identified fragments. The cloud of debris stretched across several thousand kilometers of orbit. Some fragments remained active, forming a small coma. The others appeared inactive, their volatile substances depleted or sealed beneath active crusts. These fragmentation events are crucial for predicting cosmic threats. A large comet core poses minimal risk to Earth, as the likelihood of a several-kilometer-wide core colliding with our planet is nearly zero. However, the fragmenting comet creates dozens or hundreds of pieces, each capable of entering the atmosphere. And although individual fragments are smaller and less destructive, the likelihood of one crossing Earth's path increases. Most comet fragments burn harmlessly in the atmosphere or pass by Earth, but the risk increases when it comes to dispersed debris rather than a single object. With the expected comet event in 2006, which is set to be the brightest comet of the century, current observations take on new meaning. Comets are the chaotic clocks of the solar system, appearing unpredictably, shining erratically, fragmenting without warning. They mark time in human consciousness differently than the regular movements of planets and stars. A whole generation remembers Halley's Comet in 1986, the impression of which was disappointing for most, but it held cultural significance. The generation before ours remembers the Hale-Bopp Comet, which was visible to the naked eye for several months in 1997 and was so bright that it could be seen from city centers. The current generation may remember the comets Lemmon, Swan, or Three-Eyed Atlas, depending on whether they survive to the moment they become bright enough. Are we in a period of unusual comet appearances? Statistical analysis of the rates of comet discoveries over decades shows fluctuations that may indicate a real clustering or simply reflect improvements in detection technology. A greater number of telescopes covering more of the sky with increased sensitivity naturally finds more comets. The Atlas Observatory, which discovered the Three-Eyed Atlas, exists specifically to search for near-Earth objects and finds comets as a bonus. Catalina Sky Survey, the observatory on Mount Lemmon. Pan-STARRS in Hawaii. All these automated systems constantly monitor everything that moves, and comets move, so they are found. But the data contains an intriguing hint that the Oort cloud, this distant repository of comets, may experience disturbances that direct streams of comets towards the inner part of the solar system. Passing stars, gravitational interactions with giant molecular clouds in the galaxy, even the vertical oscillations of the solar system during its orbital motion around the center of the Milky Way, all of this can release comets. If this is indeed the case, then such streams of comets will occur on timescales of millions of years, which is too long for direct observation by humans. But geological records may contain traces of impact clusters that could indicate ancient comet storms that struck the inner solar system during the time of the dinosaurs, or even earlier in Earth's history. Comets function like chaotic clocks of the solar system because they do not follow regular, predictable trajectories like planets. Most planets orbit in nearly circular paths. Their positions can be predicted with high accuracy for centuries ahead. Comets come from distant darkness on highly elliptical orbits. They return, if they return at all, after decades, centuries, or millennia. Some of them are new visitors, falling from the Oort cloud for the first time, while others are short-period comets captured by Jupiter's gravity into orbits that return them every few years. They remind us that the solar system is not a clockwork mechanism with perfect orbits, but a dynamic, chaotic environment where gravitational interactions constantly alter trajectories and new participants appear on the scene without warning. While astronomers scan the sky for comets and track solar winds, another space race unfolds in laboratories and ground stations on Earth. In 2025, China announced the completion of the world's longest quantum communication network, spanning 12,900 kilometers, connecting Beijing to remote ground stations via satellite relays, claiming that this system provides nearly invulnerable data transmission. This announcement marks an important milestone in the quantum information revolution, and if the system works as claimed, it will change the landscape of global communications and cybersecurity, affecting much more than just military or commercial applications. The main technology is quantum key distribution, which uses the fundamental properties of quantum mechanics to detect eavesdropping. The main principle is both elegant and strange. Information is encoded in the quantum states of photons, individual particles of light transmitted through optical fibers or through space between satellites and ground stations. The no-cloning theorem ensures that these states cannot be perfectly copied. Any attempt to measure or intercept photons inevitably disturbs them in detectable forms. This means that two parties using a quantum communication channel can generate encryption keys and confidently know if anyone has tried to intercept these keys during transmission. The process begins with entangled photons, pairs of particles created simultaneously and having quantum connection, so measuring the properties of one photon instantly affects the other, regardless of the distance between them. This phenomenon, famously called by Einstein spooky action at a distance, has been confirmed in countless experiments and is the basis for several proposed quantum technologies, including quantum computing and quantum teleportation. For quantum key distribution, entangled photons allow two parties to establish common random numbers that can be used as encryption keys. Implementing the hardware requires exceptional precision. Photons must be generated, entangled, transmitted, and detected with minimal loss and maximum fidelity. Optical systems must align satellite transceivers with ground stations over distances of hundreds or thousands of kilometers, while simultaneously compensating for atmospheric fluctuations, satellite movement, and the Earth's rotation. Single photon detectors must register individual particles arriving at thousands or millions per second, distinguishing real signals from background noise and dark counts of the detectors. Error correction protocols must account for inevitable imperfections while ensuring safety. China's system uses the Messier satellite, launched in 2016 and named after an ancient Chinese philosopher. The satellite orbits at an altitude of about 500 kilometers, passing over ground stations on a sun-synchronous orbit, providing regular communication windows. During each pass, which lasts several minutes, the satellite distributes entangled photons between pairs of ground stations, allowing them to establish shared encryption keys. These keys then protect ordinary data transmission using standard encryption algorithms, while the quantum channel ensures that the keys themselves have not been compromised. The recent extension to 12,900 kilometers represents a significant engineering achievement. Previously conducted demonstrations covered shorter distances or relied on reliable intermediate stations that could theoretically be compromised. The new system connects quantum channels through numerous passages of satellites and ground stations, ensuring end-to-end security on a continental scale. According to Chinese researchers, the network already serves government and financial institutions, protecting communications from current and future decryption threats. This last point is critical. Existing encryption systems that protect everything from bank transactions to secret government messages are based on mathematical problems that are computationally difficult to solve with classical computers. The decomposition of large numbers and the calculation of discrete logarithms require so much computational time that encryption hacking becomes impractical even with the fastest supercomputers. However, quantum computers, if built at a sufficient scale, will be able to solve these problems efficiently, rendering current encryption obsolete. Data encrypted today and intercepted by adversaries may be decrypted years or decades later when quantum computers reach maturity. Quantum distributed cryptography offers protection against the threat of collect now, decrypt later, as security does not rely on computational complexity but is based on fundamental physics. Western countries, especially the United States and European nations, watch with concern the progress of China in quantum communications. The MIT Technology Review's Index of Quantum Technologies for the year 2025 ranks China first in several metrics of quantum technologies, including quantum communications and quantum sensing. American research programs are working to close the gap. The Department of Energy funds test sites for quantum networks, while DARPA explores space-based quantum communication architectures. However, China's early success and significant state investments have created a quantum gap that worries defense planners and technology strategists. The political implications extend beyond mere technological competition. If quantum communication networks become the basis for future secure communications, countries without access to this technology will face potential information inequality. International agreements regulating the development of quantum technologies are still in the early stages. Questions about export control, technology transfer, and standardization remain unresolved. Some researchers advocate for open collaboration and joint development of quantum networks as a global infrastructure, similar to how the Internet evolved as an international resource. Others insist on competitive advantages and limited access, viewing quantum supremacy as a strategic asset too valuable to share. Could space quantum networks become the foundation of the future Internet? This concept includes constellations of quantum satellites providing global coverage, ground stations in every major city, and quantum relays extending range beyond line-of-sight limitations. Data will be transmitted using encryption based on quantum keys, which are constantly updated and protected from interception, even from future technologies we cannot yet imagine. This system integrates with existing fiber optic networks, creating a hybrid infrastructure where quantum channels distribute keys and classical channels carry the bulk of data. Around such advanced technology, conspiracy theories always arise, as they are so advanced and secretive. Системы распределения квантовых ключей требуют обширного тестирования и калибровки. Процессы, которые генерируют данные о статистике передачи фотонов, эффективности детекторов и уровнях ошибок. Большинство этих данных остается закрытыми или является собственностью компаний. Chinese publications describe the system's capabilities in general terms but do not provide engineering details that would allow for independent verification or reproduction. Western intelligence agencies are undoubtedly closely monitoring this program, using signal intelligence and other methods to assess the system's real capabilities compared to public statements. This opacity fuels speculation about whether the system works as claimed or if there are undisclosed vulnerabilities, with some worrying about the potential for government surveillance. The state controlling the nationwide quantum communication network gains unprecedented capabilities to monitor who communicates with whom, even if the content of the messages remains encrypted. Metadata reveals as much about communication patterns as the messages themselves, with traffic analysis uncovering social networks, tracking movements, and predicting behavior. The quantum network that records every connection, every photon transmission, every key generation event creates an infrastructure of colossal scale. The connection to the narrative of the trilogy, Atlas, is based on an interesting parallel. Just as comets carry messages from other star systems, encoded not in language, but in chemistry and isotopic ratios, people are now creating systems capable of transmitting unbreakable encoded messages across our planet. Both cases represent information that survives in hostile conditions. The chemistry of comets survives in interstellar space and solar heat, while quantum keys endure against active opposition. Both directions expand the boundaries of the possible. Comets, as natural carriers of information formed over billions of years of physics, and quantum networks as artificial carriers of information created through decades of engineering solutions. Many uncertainties remain. The current speeds of quantum key distribution are typically measured in kilobits per second, which significantly lags behind classical data transfer speeds measured in gigabits or terabits per second. Scaling quantum networks for internet traffic processing requires either a drastic improvement in photon transmission and detection efficiency or fundamentally new approaches to quantum networks. Decoherence, the loss of quantum properties due to interaction with the environment, imposes fundamental limits on how long quantum states can be preserved and over what distances they can be transmitted. Satellites help extend the range, functioning in the vacuum of space above most of the atmosphere. However, atmospheric fluctuations at ground stations still degrade transmission quality. Another issue is the security of endpoints. The distribution of quantum keys ensures secure key transmission, but these keys ultimately must be used by classical computers for data encryption and decryption. If these computers are compromised through malware, physical access, or side-channel attacks that track electromagnetic emissions or power consumption, unbreakable quantum keys will lose their significance. Security depends on the weakest link, and in any real system, such weak links are present in large numbers. The narrative of the quantum race reflects certain aspects of human nature and technological development. We compete even in understanding and using the fundamental laws of physics. Quantum mechanics, perhaps the most successful physical theory ever developed in terms of predictive accuracy and technological impact, becomes a weapon in geopolitical competition. The same quantum principles that explain atomic structure and chemical bonds now protect communications and promise revolutionary computing capabilities. Nations invest billions in quantum research not out of pure scientific curiosity, but because quantum technologies can determine military balance and economic leadership in the coming decades. The question of whether this competition will drive innovation faster than collaboration and whether the benefits of quantum networks will be distributed globally or concentrated in a few technologically advanced countries remains unanswered as the race accelerates. The circular economy within you. Science sometimes makes discoveries so unexpected and contrary to intuition that they force us to reconsider fundamental assumptions about what is possible. An announcement that synthetic biologists have created yeasts capable of converting human urine into the bone mineral hydroxyapatite represents one such discovery. Potential areas of application range from medical to ecological, with deeper implications touching on waste issues, value, and the astonishing ways biological systems can be reprogrammed to transform one substance into another. Urea, the main nitrogen-containing component of urine, serves as waste in the metabolism of mammals. When proteins break down in the body, amino acids are metabolized, and the nitrogen contained in them must be excreted. Aquatic animals excrete ammonia directly, which is a simple and energy-efficient solution when living in water that dilutes and carries away the toxic compound. Terrestrial animals face a problem. Ammonia is too toxic to accumulate, but conserving water matters, so land animals have evolved more complex solutions. Birds and reptiles produce uric acid, a relatively insoluble compound that precipitates and can be excreted as a paste, allowing for minimal water loss. Mammals produce urea, which is soluble enough for transportation in water, but less toxic than ammonia. It is excreted as liquid urine, representing a compromise between water conservation and waste removal. An adult produces about 1 to 2 liters of urine a day, depending on fluid intake and metabolism, containing about 20 to 30 grams of urea. This amounts to about 10 kilograms of urea per person per year, multiplied by 8 billion people worldwide, resulting in approximately 80 million metric tons of urea produced annually. Currently, this urea enters sewage systems, where it decomposes by bacteria or enters the environment. A new approach in synthetic biology raises the question of whether it is possible to transform this waste stream into something valuable. Hydroxyapatite is a mineral component of bones and teeth, a calcium-containing compound with the formula Ca10PO40H2. It provides strength and structural integrity, allowing bones to support body weight and protect organs. Natural bone is a composite material made of hydroxyapatite crystals embedded in a collagen protein matrix, combining the hardness of minerals with the flexibility and strength of organic fibers. Pure hydroxyapatite is required in medical applications for bone grafts, dental implants, and reconstructive surgery. Currently, hydroxyapatite is synthesized using chemical methods or extracted from animal bones. Both approaches have limitations in purity, crystalline structure, and production cost. The approach using genetically modified yeast is based on engineering metabolic pathways. Researchers identified a series of enzymatic reactions necessary for converting urea into chemical precursors of hydroxyapatite. Then genes coding for these enzymes were inserted into yeast cells. The common Saccharomyces cerevisiae, used in brewing and baking, now contains synthetic metabolic pathways that do not exist in nature. When yeast receives urine as a nitrogen source and is provided with calcium and phosphate ions, they produce hydroxyapatite crystals that precipitate and can be collected. This mechanism involves several stages. The urea enzyme breaks down urea into ammonia and carbon dioxide. Ammonia is involved in the synthesis of amino acids, while carbon dioxide and additional calcium and phosphate ions participate in mineralization reactions, forming hydroxyapatite. The precise crystallography of the product, its size, shape, and purity of hydroxyapatite crystals depend on the reaction conditions, including pH level, temperature, ion concentration, and the genetic program of yeast pathways. The initial results show promising indicators, producing hydroxyapatite with characteristics similar to the mineral components of bones, but significant optimization is needed before the process becomes practical for medical applications. Current efficiency and production output levels limit immediate applications. Yeasts produce hydroxyapatite in concentrations insufficient for commercial use, requiring large volumes of bioreactors to obtain significant amounts. Problems with purification arise from the need to separate hydroxyapatite from yeast cells, nutrient medium components, and metabolic byproducts. Purity is critically important for medical applications. Foreign particles or bacterial endotoxins in implanted hydroxyapatite can trigger immune reactions or infections. Achieving medical cleanliness from a biological production system requires strict quality control and purification protocols. Nevertheless, the potential of such technology could be revolutionary. Bone fractures affect millions of people each year, and while most heal naturally, complex fractures or loss of bone tissue due to disease or injury often require transplants or synthetic materials to support healing. Modern materials for bone grafts include autografts taken from the patient's body, allografts from deceased donors, and synthetic ceramics. Each of these options has its drawbacks. Autografts require an additional surgery to harvest the tissue. Allogenic materials have a low risk of disease transmission and immune rejection. Synthetic ceramics sometimes poorly integrate with natural bone tissue. Biologically produced hydroxyapatite from waste could become an affordable and cost-effective alternative if production and purification issues are resolved. Dental implants represent another major market. Coatings of hydroxyapatite on titanium implants enhance osseointegration, meaning the connection between the implant and the jawbone. Currently, coatings are made from hydroxyapatite, obtained through high-temperature chemical sintering, which requires significant energy costs. Biological production at room temperature in an aqueous solution could reduce energy costs and carbon footprint by creating more bone-like crystalline structures that better integrate with living tissues. The ecological benefits extend beyond the direct use of the material. Urea in wastewater contributes to eutrophication when it enters rivers and coastal waters. Excess nitrogen stimulates algae growth, leading to blooms that deplete oxygen and create dead zones. The capture of urea and its transformation into a solid mineral substance allows for the removal of nitrogen from wastewater, reducing negative environmental impact. This process represents waste recycling, treating waste as a resource rather than a disposal problem. However, there are disputes surrounding the use of human waste in medical materials. Cultural taboos on urine and feces have deep roots. Although we understand that purified compounds have no memory of their origin, psychological resistance remains. Will patients be willing to accept bone transplants or dental implants made from urine? Will regulatory bodies approve such materials for human use? These questions pertain more to cultural values and risk perception than to technical feasibility. Applications for participation in space missions are perhaps the most compelling example. Colonists on Mars or participants in long space expeditions face resource limitations, making every opportunity for recycling extremely valuable. Crew members produce urine daily, and this urine contains nitrogen and other elements that need to be processed rather than disposed of. Transforming urine into usable hydroxyapatite for medical or construction purposes kills two birds with one stone. It manages waste and produces useful products. Closed life support systems necessary for space exploration urge designers to maximize recycling and minimize waste. Your waste can literally save your life if a broken bone on Mars requires a transplant, and the only available hydroxyapatite will be obtained from the crew's urine. The resistance of large pharmaceutical companies to the implementation of cyclic biotechnology represents a predicted rather than proven conspiracy theory. Pharmaceutical and medical companies profit from current production methods and supply chains. Destructive technologies threatening existing business models face resistance, regardless of their technical feasibility. The feasibility of this resistance for hydroxyapatite obtained from urine depends on factors such as production costs, scalability, regulatory pathways, and the intellectual property market. If a technology can be patented and controlled by established players, its adoption becomes more likely. If it threatens to commercialize a high-margin product, resistance becomes more likely. Deep output goes beyond specific application. Nature knows no waste. Nutrients circulate in ecosystems. The waste of one organism becomes food for another. Energy flows, and elements circulate. People developed in cultures where waste disposal was simpler, as the population density was lower, and natural processes decomposed and recycled most waste. Industrialization and urbanization destroyed these cycles, creating waste flows that overwhelmed natural recycling capacities. Synthetic biology offers tools for artificially restoring these cycles, creating organisms to fill ecological niches that do not exist naturally but meet human needs. The transformation of urine into the mineral components of bones is just one example. The same principles apply to converting carbon dioxide into fuel, plastic waste into biodegradable polymers, and agricultural runoff into valuable chemicals. We are learning to close technological cycles, lagging behind the circular economy that nature has perfected over billions of years. Part 10. Yarn, who crosses species. The behavior of animals evokes endless admiration, as it reflects cognitive and emotional states that we recognize from our own experience, yet manifests in beings whose minds remain alien to us. Contagious yawning, a phenomenon where seeing someone yawn creates an irresistible urge to yawn oneself, was until recently thought to be unique to humans and a few other highly social mammals like chimpanzees and dogs. The publication of a study demonstrating contagious yawning in zebrafish challenges this assumption and raises complex questions about the evolutionary origins and neural mechanisms underlying this behavior. Zebrafish, small freshwater fish native to the rivers of South Asia, have become model organisms for studying the development and behavior of vertebrates, popular in both scientific research and home aquariums. Their embryos are transparent, allowing researchers to observe organ formation in real time under microscopes. The genetics of these fish are well characterized, with tools available for gene manipulation and observation of the results. They are small, inexpensive to maintain, and produce hundreds of offspring, making them ideal for large-scale experiments. But no one expected them to yawn contagiously. The experiment involved placing zebrafish in neighboring aquariums where they could see each other through transparent walls. Researchers induced yawning in a fish by depriving it of oxygen, a known trigger for yawning in many species. Cameras recorded the behavior of both the yawning fish and the observers. Analysis showed that observing fish yawned significantly more often after seeing a neighboring fish yawn, with a temporal correlation indicating true contagious yawning rather than random yawning caused by common environmental conditions. Why is this surprising? It was believed that contagious yawning required mirror neurons or similar neural circuits that allow animals to mentally imitate the actions and states of others. These chains, concentrated in the brains of primates and suspected in some social mammals, provide the neural basis for empathy, learning through imitation, and theory of mind. Fish brains lack the cortical structures where mammalian mirror neurons are located. Their neural organization is fundamentally different, simpler in some aspects, though overall not simple. The presence of contagious yawning in zebrafish suggests that this behavior does not require a complex neural structure, as we assumed, or that convergent evolution has created similar circuits in fish through entirely different anatomical pathways. The neural circuits underlying yawning in any species remain not fully understood. The act of yawning involves coordinated contraction of the jaw, facial, throat, and respiratory muscles, leading to the characteristic mouth opening, deep inhalation, and subsequent slow exhalation. This behavior seems involuntary once triggered, resistant to conscious suppression, despite the social context in which yawning may be inappropriate. There are many triggers, including fatigue, boredom, low oxygen levels, and the sight of others yawning. The variety of triggers suggests the presence of several neural pathways converging to a common motor output. In humans, contagious yawning increases during childhood development, peaks in young age, and correlates with levels of empathy. People who score high on empathy questionnaires yawn more often when they see others yawn. Individuals with autism and spectrum disorders, who often struggle with social cognition and empathy, show a reduced incidence of contagious yawning. These correlations confirm the hypothesis that contagious yawning depends on the neural systems involved in social cognition and emotional resonance. The discovery of similar behavior in zebrafish, which are usually not associated with empathy or complex social cognition, calls this clear theory into question. The evolutionary puzzle deepens when considering the taxonomic distribution. Contagious yawning is observed in humans, chimpanzees, bonobos, dogs, and now in zebrafish. It is absent or has not been demonstrated in many tested species, including cats, horses, and most birds. The scattered distribution of this behavior in the animal world suggests either multiple independent sources of origin or an ancient origin with subsequent loss in many lines. Neither of these explanations is entirely satisfactory. The convergent evolution of such specific behavior as contagious yawning in mammals and fish seems unlikely unless this behavior serves an important function that we have not identified. Its ancient origin requires an explanation for why so many species have lost it. Hypotheses about the function vary greatly. One suggestion proposes that contagious yawning serves to coordinate a group, synchronizing states of arousal or attention in social groups. If one individual notices changes in the surrounding environment that trigger yawning, it may signal a transition from wakefulness to rest. The spread of this signal among the group helps coordinate collective behavior. Schools of fish indeed require coordination. They move as a single entity, simultaneously turning, maintaining precise distance between themselves, and responding to threats with synchronized maneuvers. Could contagious yawning be part of the behavioral toolkit, enabling this coordination? Another hypothesis focuses on stress relief and social connection. Yawning may serve to regulate stress hormones or reset neural states in conditions of social stress. Observing others yawn and yawning in response can create a closed loop that helps groups collectively cope with tension. Zebrafish are social creatures that form schools in nature, with a social dynamic that includes a hierarchy of dominance, competition for mates, and vigilance against predators. Contagious yawning may play a role in maintaining group cohesion under stress. The debate is whether the behavior observed in zebrafish can be considered yawning rather than some other jaw movement or gill action misclassified. Fish do not breathe air under normal conditions, so the respiratory component of mammalian yawning has no direct analog. The wide-open mouth movement observed in zebrafish may perform various physiological functions related to gill ventilation or feeding. Critics argue that without clear evidence, fish behavior cannot be linked to the same neural triggers and physiological consequences as yawning in mammals, calling it contagious yawning, which anthropomorphizes superficially similar but functionally different behavior. Supporters argue that this behavior has key characteristics similar to mammalian yawning, including its involuntary nature, stereotypical motor pattern triggered by hypoxia, and now demonstrated social contagion. Neural pathways may differ between fish and mammals, separated by hundreds of millions of years of evolution. But if this behavior serves similar functions and responds to similar triggers, the term yawning can be considered appropriate. Biology is full of convergent evolution, where different structures perform similar functions. Bird wings and bat wings are anatomically different, but functionally equivalent. Perhaps yawning in fish and yawning in mammals represent convergent solutions to similar behavioral or physiological challenges. Speculations delve into deeper biological territories. Can contagious yawning represent a universal signal, an ancient channel of communication preceding more complex social cognition? Perhaps the basic neural scheme that makes yawning contagious evolved early in the history of vertebrates, preserved over hundreds of millions of years, as it performs fundamental coordination functions in social species. This requires that behavior brings significant advantages in survival or reproduction, so that natural selection supports it despite the costs associated with the necessary neural mechanisms. At the edge of a scientific discussion, rarely voiced in academic circles but whispered in the corridors of conferences, lies the question of whether the phenomenon of synchronization can extend beyond individual species, perhaps even across the kingdoms of life. Contagious yawning, as we now understand, occurs through sensory perception. Seeing or hearing someone yawn activates neural pathways that trigger yawning. However, a broader synchronization in nature occurs through mechanisms we are just beginning to understand. Heart cells grown in culture synchronize their rhythms through electrical and chemical signals. Fireflies in the mangrove forests of Southeast Asia synchronize their flashes among hundreds of individuals. Can deep biological principles of synchrony and resonance exist, manifesting in contagious yawning and other phenomena? The connection to cosmic themes is made through the concept of resonance and synchronization on different scales. Schools of fish move like coordinated units, responding to each other's movements through their lateral line, which detects changes in water pressure. Flocks of birds turn simultaneously, each following simple rules of spacing and alignment, resulting in complex, emergent patterns. On a large scale, the planet moves in resonances, with gravitational interactions fixing their periods in whole ratios. The moons of Jupiter, Europa, Ganymede, and Io are in a 4:2:1 resonance, where each orbital configuration repeats. On a cosmic level, clusters of galaxies move under mutual gravitational influence, their dynamics connected over millions of light years. Synchronization serves as a fundamental principle, organizing systems from molecular to cosmic levels. Oscillators, whether neurons, hearts, swinging pendulums, or planets, strive for phase synchronization, tuning their rhythms to common frequencies as they interact. The mathematics of coupled oscillators reveals astonishing similarities between different physical systems. Perhaps contagious yawning is a biological interpretation of these universal principles of synchronization, a social oscillator that connects through observation and triggers synchronized reactions. Human brains and stars may have more in common than we think if we shift our perspective from specific mechanisms to abstract principles. Both represent complex dynamic systems with internal structures, emergent properties, and connections to the external environment. Both process information, although in completely different ways and on significantly different scales. The brain processes sensory inputs and generates behavioral outputs through electrochemical signaling in neural networks. Stars process gravitational inputs and produce radiation outputs through nuclear fusion, regulated by hydrostatic and thermodynamic equilibrium. The analogy quickly loses meaning if overloaded, but it raises deep questions about complexity, information, and organization in the universe. The study with zebrafish essentially reminds us how little we truly understand about consciousness and animal behavior. Every assumption, every supposedly established fact about what animals can and cannot do, remains conditional and subject to revision when new evidence emerges. We believed that contagious yawning requires empathy and mirror neurons. Fish, it seems, did not receive this message. What other behaviors that we consider uniquely human or uniquely mammalian may have deeper roots or a broader distribution than we realize? Tool use is observed in birds and octopuses. Culture, defined as learned behaviors passed socially through generations, exists in whales and crows. Metacognition, thinking about thinking, is exhibited in rats and dolphins. The more we explore, the more we discover that the boundaries we draw between humans and other animals, between complex and simple minds, blur upon closer examination. Part 11. A stone that glides through the Earth's atmosphere. April 13th, 2029 will be a date that humanity remembers, if, of course, we are still here to remember anything. On this day, asteroid 99942 Apophis, named after the ancient Egyptian demon of chaos and darkness, will pass by Earth at a distance of 31,000 kilometers. In comparison, geostationary satellites orbit at an altitude of about 35,000 kilometers. The Apophis will pass inside the ring of satellites responsible for weather forecasting, communication, and navigation through the global positioning system. It will be visible to the naked eye as a rapidly moving point of light against the stars. The first time in history that an asteroid of this size approaches Earth so closely that ordinary observers can see its passage. Current orbital calculations do not predict collision risks. The close approach of Apophis is inevitable, its trajectory well studied, and it will safely pass by our planet, avoiding collision. This confidence is the result of decades of careful observations and orbital refinements. When Apophis was discovered in 2004, initial trajectory calculations did not rule out a small but non-zero chance of collision during its pass in 2029. This statement caused a brief public stir and intense interest among scientists. Subsequent observations as the asteroid appeared in different parts of its orbit refined the calculations, narrowing the uncertainty zone the area where the asteroid could be at any moment, to completely eliminate the possibility of a collision in 2029. But the story does not end in 2029. A close passage will alter Apophis's orbit due to gravitational interaction with Earth. When the asteroid passes near the planet, tidal forces and gravitational acceleration change its trajectory, sometimes quite significantly. The degree of change depends on how close the approach is and the relative speeds. Apophis will experience a significant orbital deviation, altering its period of revolution around the Sun and changing the potential for future intersections with Earth. Forecasts for the upcoming close approaches in 2036 and 2068 are tied to significant uncertainties, as these future positions depend on the precise details of the encounter in 2029, which we cannot measure accurately until the meeting occurs. The distance, closer than geostationary orbit, makes this an unprecedented scientific opportunity. Telescopes will continuously track Apophis as it approaches, measuring its rotational state, mapping its surface, determining its composition through spectroscopy, and measuring its size and shape using radar. The diameter of the asteroid is about 370 meters, which is enough to cause regional destruction in the event of a collision, but not enough to make observing its surface from Earth difficult. A close approach allows the use of methods typically applied to objects nearer to Earth during even closer encounters. Radar astronomy will play a key role. Radio telescopes, such as the Goldstone antenna in California and the replacement for the Arecibo Observatory, if operational by then, will be able to reflect radio waves from the surface of the asteroid and analyze the echo. The radar provides precise distance measurements accurate to meters, rotation period measurements accurate to seconds, and surface roughness information that optical telescopes cannot provide. Imaging using Doppler radar delay creates two-dimensional images, where one axis represents distance and echo time delay, and the other represents speed, the change of the Doppler effect of the echo. These radar images show the shape, rotation, and surface features, sometimes revealing boulders, craters, and ridges just a few meters in diameter. Studying the rotation of asteroids is important as their speed and rotational states contain information about their history. The asteroid Apophis rotates with a period of approximately 30 hours, as determined by light curves showing how its brightness changes depending on which facets reflect sunlight towards Earth. Currently, this rotation speed is stable, but the encounter with Earth in 2029 will change it. The asteroid's approach to Earth will cause tidal forces that will affect its rotation, potentially speeding it up or slowing it down depending on the geometry of the collision. Measuring the changes in rotation provides data about the internal structure of the asteroid, whether it is a solid monolith or a loose pile of small fragments held together by gravity. The Arkowski effect adds another layer of complexity. Asteroids absorb sunlight, heating their surfaces, and then redistribute this energy as infrared heat. Thermal radiation carries momentum, creating a small rocket effect that propels the asteroid. The warm side of a rotating asteroid is hotter after noon than in the morning, and the asymmetric thermal radiation creates a small but constant force that either accelerates or decelerates its orbital movement depending on the direction of rotation. For millions of years, the Arkowski effect can significantly alter orbits, moving asteroids from the main belt into trajectories that cross Earth. To predict its long-term orbital evolution, precise measurements of the Arkowski effect are necessary. The effect is small, creating orbital changes of just a few meters per year, but these meters accumulate over decades, leading to kilometers of uncertainty in positioning. A close approach in the year 2029 provides the opportunity to measure the acceleration of Arkowski by comparing the actual position of the asteroid with predictions that do not account for thermal effects. Any deviation indicates the influence of Arkowski and allows for the calibration of models used to predict future encounters. Public perception presents both a challenge and an opportunity. The asteroid Apophis has repeatedly made headlines since its discovery, usually accompanied by alarming phrases about deadly asteroids and cosmic threats. In fact, the risk of collision is low or practically non-existent for all calculations made so far, but communicating about risks is a complex task. Explaining that the probability of a strike in 2068 is 1 in 45,000. Current assessment means different things to different people. Statisticians see it as a minor risk, much smaller than many risks we face daily. But to someone unfamiliar with probabilities, 1 in 45,000 sounds alarming, like a real threat rather than a practically impossible event. Proposals for missions to the asteroid Apophis are being discussed in the community focused on planetary defense. Sending a spacecraft to approach the asteroid during or after its encounter with Earth in 2029 will allow data to be collected that cannot be gathered from Earth. The mission will be able to detail the composition of the asteroid, its internal structure, and surface. It may also serve as a demonstration of deflection technologies, using methods such as kinetic impact or gravitational tractor to slightly alter the orbit of Apophis and prove that we have the ability to protect Earth from future asteroid threats. NASA's mission called DART, which tested the double deflection of an asteroid in 2020, successfully collided with the asteroid Dimorphos, demonstrating that kinetic deflection works as expected. The impact changed the orbit of Dimorphos around its larger companion Didymos, confirming that humanity can alter asteroid trajectories with enough warning time. The mission to Apophis will rely on the success of DART, testing deflection technologies on a larger and potentially more scientifically interesting target. There are conspiracy theories suggesting that NASA downplays the likelihood of a collision, which is predictable but psychologically understandable. Space agencies face a difficult task, finding a balance between transparency and preventing panic. The publication of all preliminary orbital calculations with accompanying uncertainties raises concern when these uncertainties are large, although significant uncertainties are normal for newly discovered objects with limited observational data. Waiting for announcements until the calculations are clarified carries the risk of accusations of information concealment if someone discovers the object independently or if leaks occur. NASA and other agencies typically strive for transparency by publishing orbital calculations and collision probabilities through the Sentry system and the Torino scale, but transparency does not prevent conspiracy theories. She merely shifts the focus from hiding information about clashes to concealing failures in deviation or the involvement of aliens. The narrative of an asteroid passing close to Earth reflects a mix of danger and admiration. Close approaches inspire. Apophis will not collide with us, but it will pass close enough for us to feel its presence, observe its movement, and see the cosmic machine that occasionally delivers mountain masses to the vicinity of Earth. This close passage reminds us that space is not empty, that debris from the formation of the solar system still orbits, and occasionally these fragments cross paths with Earth. Despite our luck so far, fortune is not eternal. Preparation matters. The abilities to detect, track, characterize, and deflect are humanity's insurance policy against the cosmic lottery that could ultimately lead to a collision. This event also serves as a global lesson. Protecting the planet requires international cooperation. Asteroids do not recognize borders, and a threat to one nation is a threat to all. The United Nations Committee on the Peaceful Uses of Outer Space coordinates international efforts to track near-Earth objects and develop response measures. The flyby of the asteroid Apophis in 2029 is likely to spark new interest in funding and policy for planetary defense, potentially accelerating the development of detection networks and deflection technologies. Looking ahead to the planetary parade of the 2040s, one can see a broader picture. The universe operates on schedules that disregard human timeframes. Asteroids arrive when orbital mechanics dictates. The planets align according to Kepler's laws. Comets fall from the Oort cloud under the influence of gravitational disturbances that began millennia ago. We mark these events in calendars, anticipating them, preparing for them, but they unfold according to physical laws, not human convenience. Apophis will pass in 2029 regardless of whether we observe it, worry about it, or are ready. The indifference of the cosmos to human experiences instills both fear and liberation. Part 12. When the Planets Dance. September 20th, 2040. Mark it in any calendar system that can survive these years, for on this day, the solar system will present a geometric configuration, rare enough to attract attention, yet common enough for such formations to recur with predictable frequency. 6 planets, Mercury, Venus, Mars, Jupiter, Saturn, and Uranus will occupy a relatively narrow band of the sky, as seen from Earth. Their longitudes and angular positions along the ecliptic will be separated from each other by less than 90 degrees. The media will undoubtedly call it planetary alignment or a parade, although technically, the planets will not line up in a straight line. They will simply concentrate in one region of the sky, simultaneously visible from the night side of the Earth. The geometry works like this. The planets revolve around the Sun in roughly the same plane, the ecliptic, defined by Earth's orbital plane. From our perspective, the planets move along a path that crosses the sky, following the signs of the zodiac. Sometimes planets are distributed across the ecliptic, visible at different moments in time as the Earth rotates. At other times, their orbital positions are grouped so that several planets appear simultaneously in one region of the sky. These clustering events occur regularly, but irregularly. This is the result of planets with different orbital periods, sometimes aligning in specific positions. The rarity of such phenomena depends on how many planets we need to participate and how strictly we define the alignment. Gathering all 8 planets within 90 degrees happens every few decades. Fitting them within 30 degrees is possible every few centuries. Achieving actual alignment in a straight line, when all planets are at zero angular distance from the Sun, is unlikely to ever occur within human timescales, as orbital periods do not have exact whole number proportions that could create perfect recurring alignments. An event anticipated in the year 2040 will be particularly favorable for observation, as bright planets visible to the naked eye will align. Mercury, Venus, Mars, Jupiter, and Saturn. They will all be easily distinguishable without optical instruments, while Uranus, which will require binoculars or small telescopes to observe, will also participate in this phenomenon. Neptune will be on a different part of its orbit and will not take part in the gathering. The planets will be visible in the evening sky after sunset, rising together in the east and tracing an arc across the southern sky, depending on the observer's latitude, providing hours for observation. Astronomy enthusiasts will have a great time. It will become possible to capture all visible planets in a single wide-angle shot during this event, creating images that showcase the architecture of the solar system. Different brightnesses and colors of the planets add visual interest. Venus shines bright white, Mars is distinctly orange-red, Jupiter is yellowish-white, Saturn resembles Jupiter but is slightly less bright, and Uranus is barely visible as a pale bluish-green disk even through binoculars. The shot of them together creates a portrait of planetary diversity compressed into one frame. Professional astronomers will utilize opportunities beyond beautiful images. Planetary alignments do not create any special gravitational effects, despite persistent myths about tidal forces or seismic triggers, but they provide an opportunity to conduct simultaneous measurements on several planets using the same tools and methods. Comparative planetology benefits from such opportunities. Measuring the atmospheric properties of Venus, Jupiter, and Saturn during a single observation controls instrumental and observational variables, allowing for more confident comparisons. Alignment can also provide opportunities to detect unusual objects. When planets cluster together, the background star field in that region is observed more intensely than usual. Vague asteroids, distant comets, or even undiscovered planets in the far solar system can be spotted by observers scanning the region for planets. The hypothetical Planet 9, proposed to explain the orbital clustering of distant trans-Neptunian objects, has still not been discovered despite searches. The presumed location, if it exists, slowly moves through the zodiac and may be near a cluster of planets in the year 2040, making detection more likely as more telescopes will be aimed in that direction. The mythological and cultural context of planetary alignments has surrounded humanity throughout history. Ancient astronomers closely tracked the positions of planets, marking conjunctions and alignments, attributing significance to these events. Astrological traditions that continue to exist despite the lack of scientific support attribute meaning to planetary configurations based on symbolism and perceived correlations. The scientific worldview rejects these associations as an attempt to see patterns in random coincidences. Yet the human psychological reaction to celestial alignments remains strong. When the planets gather in one part of the celestial dome, it feels significant, even if we rationally understand that it's just orbital geometry. Some marginalized communities will inevitably begin to predict catastrophic consequences from the alignment in the year 2040. The supposed influence of planetary gravity causing earthquakes or climate disasters is a recurring end-of-the-world scenario without scientific basis. The gravitational impact of the planets on Earth is negligible compared to that of the Moon and the Sun. Even when the planets align, their combined gravitational pull only makes slight changes to Earth's orbit, which do not measurably affect geological or atmospheric processes. But facts do not hinder predictions, and somewhere on the internet, someone claims that this alignment will cause disasters. Other people begin to believe it and prepare. And when the disasters do not occur, these predictions will be quietly forgotten or justified. Hidden scientific possibilities arising from the alignment of planets include measurements of mass distribution in the solar system. Accurate tracking of planetary positions allows for testing gravitational theories and refining planetary masses. Each planet gravitationally influences every other planet, creating changes in their orbits that accumulate over time. By measuring the positions of planets and comparing them with where they should be, according to Newtonian gravity, astronomers can discover anomalies that may indicate unknown masses in the solar system, or, more speculatively, deviations from the gravitational theory itself. The cultural dimension of aligning global events matters in an increasingly interconnected world. Unlike solar eclipses, which are visible only from specific geographical points, planetary configurations can be observed worldwide, weather permitting. This creates shared impressions between cultures and continents. In the year 2040, people in Tokyo, New York, Sydney, and Lagos will see the same planetary alignment, creating a moment of cosmic community that transcends political and cultural boundaries. The comparison to a planetary choir works metaphorically. Each planet moves at its own pace. Mercury orbits the Sun in 88 days, while Neptune takes 165 years. These different periods create complex rhythms and patterns over time. When the planets align, it resembles a moment in a long cosmic symphony when several instruments play together, creating a chord before diverging into individual melodies. A metaphor should not be taken too far, as planets do not actually produce sounds or create music, but it reflects something true about the patterns and rhythms in orbital dynamics. The eclipse of the supermoon in the year 2052 creates continuity in the narrative. These events of alignment and close approaches mark time in ways that transcend individual human lives. A person born in 2040 will be 12 years old when the supermoon occurs, 20 when the comet flies close, and will reach middle age before the next significant planetary alignment. These cosmic events serve as milestones in generational memory, shared experiences that define eras and structure historical time beyond human constructs like decades and centuries. Part 13. The Moon Touching the Earth. November 9th, 2052 will be the day when the Moon approaches Earth at its closest distance of the 21st century. It will be a supermoon, so unusual that it will be hard to fit it into conventional definitions. The Moon's orbit around the Earth is not circular but elliptical, meaning the distance between the Earth and the Moon varies from about 363,000 kilometers at perigee, when the Moon is closest, to about 405,000 kilometers at apogee, when it is farthest. This change in distance causes the visible size of the Moon from Earth to change. When the Moon reaches perigee during a full moon, it appears largest and brightest, which we call a supermoon. The supermoon of November 2052 will be at an exceptional perigee, coming within approximately 356,500 kilometers from the center of the Earth, which is about 3% closer than typical supermoons and 6% closer than average full moons. This distance may seem insignificant in percentage terms, but it is important to remember that we are comparing angular sizes, which depend on distance in a nonlinear way. Reducing the distance by 6% leads to an increase in the visible diameter by approximately 13% and a brightness increase of 30%. The Moon will appear large at this close distance, making the size difference compared to average full moons noticeable even without tools. If you place a photograph of the full moon from the year 2052 next to one taken from a medium distance, the difference becomes obvious. The supermoon occupies more space in the sky, its details appear larger, and its brightness dramatically illuminates the landscapes. Under perfect atmospheric conditions, when the Moon is near the horizon, the combination of its enlarged real size and optical illusion will create views that seem almost surreal. The photographic opportunities will be incredible. Lunar photographers await supermoons to capture the Moon against natural landscapes, using the enlarged size of the Moon to create stunning compositions. The event of the year 2052 will be an outstanding opportunity for this generation of photographers. Preparation will begin years before the event. Locations will be chosen where the Moon will rise or set behind interesting foreground objects, and the exact time and positions for the perfect shot will be calculated. The increase in the brightness of the Moon has implications not only for aesthetics. The moonlight is bright enough to cast shadows and influence the behavior of nocturnal animals. The supermoon light is even brighter, potentially casting clear shadows from objects and illuminating landscapes to levels close to twilight. Nocturnal animals that plan their activity according to the phases of the moon may react to unusual brightness. Predators that hunt using sight can gain an advantage over prey that rely on darkness for cover. The behavior of prey may change, staying hidden during the brightest hours. Extreme tides are the most significant physical consequence of the moon's close approach. Ocean tides arise from the gradient of gravitational pull. The difference in the gravitational influence of the moon on the near side of the Earth compared to the far side creates two tidal bulges, one facing the moon and the other opposite it. The rotation of the Earth shifts coastlines across these bulges, resulting in the familiar twice-daily tidal cycle. The strength of the tides depends on the distance to the moon. The closer the moon, the stronger the gradients, and consequently, the higher the tides. Spring tides reaching their peak during new moons and full moons, when the sun and moon align, will be amplified during the supermoon in the year 2022. Coastal areas already experiencing high spring tides will see the water level a few centimeters higher than usual. This may seem insignificant, but during a storm, those extra centimeters can be the deciding factor between whether the water stays in the riverbeds or overflows the protective walls and floods the coastal infrastructure. Warnings about floods are likely to be issued in vulnerable areas, especially those already suffering from rising sea levels due to climate change. Speculations about seismic interactions enter a more uncertain realm. Some researchers studied the statistical correlations between the phases of the moon and tidal forces with the occurrence of earthquakes, seeking evidence that tidal loads on faults could trigger earthquakes that were already close to rupture. The main consensus is that any such effect, if it exists at all, is insignificant. Faults break when the accumulated tectonic stress exceeds the friction keeping them locked. Tidal forces are much weaker than tectonic ones, but for faults already on the brink of destruction, even minor additional stresses could theoretically act as a trigger. Research has shown weak correlations between tides and earthquakes in some fault systems, but not in others, and the effects were so small that they are hard to distinguish from statistical noise. The supermoon in 1022 will be a natural experiment. If tidal forces truly exist and can be measured, one can expect a slight increase in the number of earthquakes worldwide on days when the moon is closest to the Earth. If the readings remain within normal limits, this will further confirm the conclusion that tidal effects on seismicity are negligible. The cultural reaction to the supermoon will likely include both celebrations and anxiety. Festivals and events for moon observation will gather crowds in dark sky locations and at famous landmarks. Lunar eclipses coinciding with supermoons become media events attracting millions of viewers. Even without the eclipse, the record nature of the event in the year 2022 will spark interest. At the same time, various doomsday predictions and apocalyptic interpretations will circulate online, claiming that the close approach of the moon heralds disasters. These predictions follow predictable patterns and will, accordingly, be predictably wrong, but for a time will attract attention and cause unnecessary anxiety among people unfamiliar with astronomical facts. The phrase, "a night shining like day," is an exaggeration, but it accurately conveys the quality of bright moonlight. Human eyes adapt to darkness, pupils dilate to gather more light, and photoreceptive cells increase their sensitivity. With full adaptation to the darkness, the sensitivity range of human vision spans many orders of magnitude. Under a normal full moon, the moonlight provides enough illumination for a comfortable walk, reading large text, and blurred colors. The light of the supermoon pushes this further, potentially allowing for reading ordinary text and perceiving colors more vividly. Combined with high atmospheric clarity and a dark surrounding environment, such lighting approaches the level of deep twilight. Atmospheric scattering studies benefit from bright moonlight, as lunar illumination serves as a stable light source for measuring atmospheric properties. Research groups studying aerosols, clouds, and atmospheric chemistry sometimes use moonlight for calibration or to continue observations beyond daylight hours. The supermoon provides an unusually high signal level, potentially allowing for more accurate measurements or detection of subtle effects that are usually below detection thresholds. Citizen science projects can coordinate global observations of the supermoon, collecting data on visible brightness, color, and atmospheric effects from observers around the world. Such projects successfully gathered observations of eclipses, meteor counts, and reports of auroras, creating datasets that complement professional observations and engage the public in astronomy. The supermoon is an accessible target that anyone can observe and photograph, lowering barriers to participation. The shift to discussing comets that could overshadow even this supermoon sets the final accents of the story. The moon at its closest approach will be spectacular, but this is a regular phenomenon, the closest of a continuous series of supermoons that occur monthly and in varying scales. Comets are unpredictable guests that may occasionally rival or exceed the brightness of the moon, but they do so rarely and without reliable schedules. The comparison highlights different types of cosmic phenomena: predictable cyclic movements of bodies in regular orbits, and chaotic, intermittent appearances of comets falling from deep darkness. Part 14, 2060, the brightest comet in history. In 2006, an event will occur that no one living has ever witnessed. Predictions have been made, orbital calculations completed, and astronomers mark in their calendars an event that can rival any known case in history. In the distant Oort cloud surrounding our solar system, a massive object is moving towards the inner solar system on a trajectory that will bring it close enough to the sun to become spectacular. Not just bright and visible, but potentially as luminous as the moon, dominating the night sky for several weeks or even months. If the forecasts come true, this comet will become the astronomical event of the century, a unique spectacle visible even during the day, casting shadows at night and radically changing the perception of the sky for everyone who witnesses it. For clarity, most comets passing through the inner solar system are quite dim and require binoculars or telescopes for observation. Every decade, only a few become visible to the naked eye, appearing as blurred spots of light with slight tails. Every few decades, we witness a bright comet that makes headlines and causes people to go outside to look up. The Hale-Bopp comet in 1997 became one of those comets, visible for over 18 months and bright enough to be easily seen even from cities despite light pollution. Before this, the West Comet amazed spectators who woke up before dawn to see it. And of course, there is Halley's Comet, which returns every 75 to 86 years and has been documented by people for over 2,000 years, mentioned in Babylonian records, Chinese chronicles, and on the Bayeux Tapestry. However, even at its best, Halley's Comet is just a bright comet. It impresses, of course, but does not dominate the sky. The comet of the year 2060, if it meets expectations, will be able to do that. Modern models suggest that it could reach a visible stellar magnitude of -10 or even -12, making it as bright as a half moon or possibly a full moon. To understand what this means, one must know that the scale of stellar magnitude is logarithmic and inverse. The Sun has a visible magnitude of -26.7, the full moon is -12.7, and Venus at its maximum is around -4.9. A bright comet like Hale-Bopp reached about -1. Each step represents about 2.5 times more light, so a comet of magnitude -10 is not just twice as bright as Hale-Bopp, but thousands of times brighter. What creates such an impressive comet? Size matters, of course. The core of the comet of the year 2060 is estimated to be absolutely enormous, possibly between 50 to 100 kilometers in diameter, making it one of the largest objects ever to visit the inner solar system from the Oort cloud. In comparison, the core of Comet Hale-Bopp was about 60 kilometers in diameter, and that was already considered huge. But size alone is not enough. The comet must also pass close to the sun, close enough for the solar heat to vaporize massive amounts of ice, creating a coma that can grow larger than Jupiter, and a tail that can stretch for hundreds of millions of kilometers. The comet of the year 2060 corresponds to all these criteria. The perihelion of the comet will bring it to a distance of about 0.3 astronomical units, which is approximately 45 million kilometers, the inner part of Mercury's orbit. At such a distance, the warmth of the sun will evaporate not only water ice, but also more volatile compounds like carbon monoxide and carbon dioxide. But beyond science, something deeper is happening here. In one brief minute, in the year 2026, humanity will share a common experience. People in every country on every continent will look up at the sky and see the same thing. A comet so bright that it cannot be ignored, so impressive that it transcends barriers of language, culture, and politics. The comet of the year 1026 will be impossible to miss. It will dominate the twilight and night sky, visible even from bright cities, emitting enough light to read in the dark. And here begins the most interesting, perhaps a bit unsettling part. What happens when a light source comparable to the moon appears in the night sky? We know that moonlight affects ecosystems. Nocturnal animals change their behavior depending on the phases of the moon. Predators hunt differently during full moons. The circadian rhythms of humans, internal clocks regulating our sleep and wake cycles, are influenced by the level of surrounding light. Throughout humanity's existence, the moon has remained the brightest object in the night sky. What happens if a third variable is added to the equation? The truth is, we do not know this. The comet will be visible for several weeks, possibly months, and during this time it will emit light into the night environment at levels that Earth has not experienced from comets in known history. Now let's discuss less pleasant possibilities. When the comet approaches Earth, people begin to worry about collisions and disasters. Let me clarify. The comet of the year 1026 will not collide with Earth. Its orbit is well known, and it will pass by us millions of kilometers away. But that doesn't mean it is completely harmless. Comets lose material as they approach the sun. Dust, small particles, and sometimes even larger fragments break off and scatter along the comet's orbit. If Earth's orbit intersects with a comet's after its passage, we might encounter a stream of debris, leading to a spectacular meteor shower. But there is a more troubling scenario, which, although unlikely, cannot be ruled out. Comets sometimes break apart as they approach the sun. Thermal stress, tidal forces, gas pressure, all of this can lead to the destruction of a comet's core. If the comet of the year 1026 breaks apart, and one of the fragments ends up in an orbit that brings it closer to Earth than predicted, we will have a problem. The probability of this is extremely low, but it is not impossible. That is why tracking asteroids and comets has become such a serious matter. But I hope the dominant reaction will be admiration. Because, whatever happens, the comet of the year 1026 will be beautiful. This will serve as a reminder that we live in a universe capable of creating spectacular phenomena. For weeks or months, the structures of tails and the dynamics of comas will be discussed over dinner. Children will stay up late to see the comet. She will enter the cultural context of her generation, and when it all ends, when the comet orbits the sun and begins its journey back to the outer part of the solar system, we will have photographs and memories. But even as it disappears from view, another date will appear on the cosmic calendar, representing a no less significant milestone. The year 2177, the first birthday of Pluto and cosmic contemplation. On the 18th day of February 1930, a young astronomer named Clyde Tombaugh was studying photographic plates at the Lowell Observatory in Flagstaff, Arizona. He was searching for the predicted ninth planet, a world beyond Neptune that could explain small deviations in the orbits of the outer planets. The work was exhausting. He compared pairs of photographs taken days apart, looking for something that moved against the backdrop of stars. And so he found it. A tiny dot that changed its position between exposures. Planet X, the ninth planet, Pluto. This discovery became a sensation worldwide. Pluto became the first planet discovered by an American, capturing the public's imagination in a way that rarely happens with astronomical discoveries. The name Pluto, suggested by an 11-year-old girl from England named Venetia Burney, seemed perfect. The god of the underworld for the distant dark world at the edge of the solar system. For 76 years, school children were taught that there are 9 planets in the solar system, with Pluto, tiny and mysterious, being the last outpost before the great darkness of interstellar space. In 2006, the International Astronomical Union redefined what it means to be a planet. Pluto met 2 of the 3 criteria, but failed the third, as it did not clear its orbital zone of other debris. According to the new definition, Pluto was reclassified as a dwarf planet, and the solar system returned to 8 planets. This downgrade sparked an unexpected public reaction. People felt sympathy for Pluto, this distant and unprotected world. But here is something that puts all this in perspective. In the year 2377, 247 years after its discovery, Pluto will complete exactly 1 orbit around the Sun, returning to the same position in space where Clyde Tombaugh first noticed it on those photographic plates. Consider what this means. A year on Pluto, the time needed to complete 1 orbit, is 247.9 Earth years. When Pluto was discovered in 1930, it had completed about 36% of an orbit since the signing of the Declaration of Independence. We discovered Pluto, studied it, sent a spacecraft that flew past it in 2015, observed its decline, and discussed it. Throughout all this time, Pluto has not completed a single orbit around the Sun. This is a profound lesson about timescales. We, humans, live, at best, around 80 to 100 years. This time is available for the direct memory and experience of each person. Our civilizations exist significantly longer, with continuous written records going back about 5,000 years. However, even on this timescale, Pluto has completed only about 20 orbits. The entire history of human civilization encompasses just 20 journeys around the Sun for this distant world. If we look more broadly at the history of the solar system, which spans 4.5 billion years, Pluto has completed about 18 million orbits. This seems significant until we realize that Earth has completed 4.5 billion orbits in the same time. But it's not just about Pluto. The outer part of the solar system operates on timescales that exceed human experience. Neptune completes one orbit around the Sun in 165 years. Since its discovery in 1846, Neptune has completed just over one orbit. Uranus does this in 84 years, and Saturn in 29. These worlds move through the zodiac with a majestic, almost imperceptible speed. Ancient astrologers knew only of 5 planets beyond Earth, as they are the only ones visible in a human lifetime. This raises an interesting question. What is the longest timescale that a human can truly comprehend? We can intellectually understand that the universe is 13,800,000,000 years old, that the Sun formed 4.5 billion years ago. We can pronounce these numbers, place them in textbooks, teach students. But do we truly perceive them? Can the human mind hold 13 billion years of time in such a way that it seems real? Probably not. Our intuition is tuned to human lives, to the years we expect to live. Beyond a few generations, time becomes abstract. That is why the first birthday of Pluto after its discovery is such a significant event. It is a timescale that our civilization can barely comprehend. 247 years span from the year 1777 to 2177, more than a century and a half into our future. This is longer than the life of any person, longer than most institutions have existed, but short enough for us to trace cultural continuity. People in the year 2177 will be able to look back at records related to the discovery of Pluto and understand what astronomers did and why it mattered. But when Pluto completes its first orbit in 2177, it will only begin its second orbit from the moment of discovery. This second orbit will take another 247 years. Pluto will not complete its third orbit until 2671. The people who will witness Pluto's second birthday have not yet been born and will not appear for centuries. By then, will people still care about Pluto? Will we continue to watch the sky, tracking planets, and marking these cosmic milestones? I would like to believe that we will be. Despite everything, despite the chaos that often characterizes human behavior, we have maintained astronomical observatories for centuries. We have accumulated knowledge, passed it down from generation to generation, building on the discoveries of our ancestors. The fact that we can calculate the orbit of Pluto and predict its position in the year 2177 is a testament to the strength of accumulated human experience when people work towards common goals over centuries. Speaking of long time spans, consider the following. When the comet Tri-I Atlas entered our solar system in the year 2024, it had traveled through interstellar space for millions of years. If it were ejected from a star system 10 light-years away and traveled at a speed of 66 kilometers per second, it would take about 45,000 years to cover that distance. All this time, the comet remained frozen, unchanged, drifting in emptiness, then spent several months in our solar system, was destroyed by the sun, and vanished. However, understanding is not the same as experience. We can calculate Pluto's orbit, but we cannot feel what it is like to make a complete circle around the sun in 247 years. We can measure the sun's life in 10 billion years, but we are unable to deeply comprehend this time span. We are limited by our biology, mortality, and our place in time and space. When Clyde Tombaugh discovered Pluto in 1930, he was 24 years old. He passed away in 1997 at the age of 90, having lived to see spaceships visit all the planets in the solar system and watched as humans set foot on the moon. But he never saw Pluto complete its orbit. No person alive when Pluto was discovered will live to see its first birthday. This important moment will belong to those yet to be born.